Hey, welcome back. Hope you enjoyed the video. I usually show some of the TED video. You know what's TED Talk, right? TED Talk is some like inspiring or high tech or high meaningful video. You can go there. One of the series is called TED Ed. Here. The TED Ed actually quite interesting. If a lot of different riddles, facts, or whatsoever. Okay. So I don't know, you know that what was the new word for last year? It's called brain rot. Okay, but everyone loves brain rot because you just like to wipe those. But I would suggest if you want to really spend your time relaxing, you can actually watch some of these instead of just somebody leaking soy sauce in the sushi store. Okay, so it's more beneficial and more interesting. So what just now, actually the video is highly related to our course. Yeah. Okay, so I highly encourage you that because what happened is it's actually called a Hamiltonian path problem. Yeah, okay. It's quite simple. The question is just, if you have a graph, can you find a path that visits every vertex without repeating? Okay, sometimes it's possible, sometimes it's not possible. And how do you find the path? In mathematics, the answer to what is the path and is it possible or not possible are two separate questions. You can actually just tell that, oh, it's possible or not possible without finding the path. Okay, sometimes you can do that. But of course, if you find the path, then you know that it's possible. But if you cannot find the path, how can you prove it's not possible? So these two are two separate questions. And actually, because we are in a class of data structure and algorithms, I know you may not reach that level, but there's one thing about this one. Okay, where is that? This one. This is actually the core nucleus soul of computer science. Computer science, the first question is actually asking, is the problem solvable? So you use computer for anything. People ask, what is computer science? Computer science now is AI. Computer science is now, in the past few years, it's like writing apps. It's like bioinformatics. Computer science is a web page. Computer science is whatever, okay? But actually the real core middle, so the central of computer science is about, can you compute it? Because if you cannot compute it, how do we tell, how can we arrange an algorithm, arrive at an algorithm to solve it or whatever, okay? So I don't know anyone heard of this term before, NP complete? Anyone heard of that? NP hard, NP complete? No. Actually, NP complete and NP hard stand for some of the problem cannot be solved in polynomial time. So NP, non-polynomial time algorithms. Is it okay? What we are studying is polynomial time algorithm. Quicksort, n squared, n or n. Those are polynomial time algorithms. But some of the problem are so-called stated that they are non-polynomial type. For example, they are like 2 to the power n. They're algorithms, like exhaustive search. But actually, the big question is, I think I mentioned it before. Are all these non-polynomial time algorithms, can we really unable to solve them in polynomial time? So this is actually a big question, still open. Why? I tell you what, there's a lot of non-polynomial time algorithms like this traveling salesman. There's another problem like the logic satisfaction. There's a lot of this type of problem. They all cannot solve. But we all face one problem. I think I also mentioned it before. Is it these problems are really that hard? Is really non-polynomial time? Or is it just human race is still dumb? What does that mean? You know, we are human race, a lot of time we are just dumb. At the first time, we thought the material are being separated by atoms. We thought we are very smart. We discover atoms. And then later on, we discover, oh, inside atom, there's electrons, neutrons. We thought that we reached the heaven already. We finished everything. We know all things about universe. And then now we know that there's subparticles. And at first, we think that we are in a 3-dimensional space. Later, we discover we are 4-dimensional space. And then we are thinking, oh, 11-dimensional space, 26-dimensional space in string theory. And no one can even tell now is light a particle or a wave. Okay, so here is that we are so dumb we don't know that there's actually a polynomial time solution, or is it really non-polynomial time? Okay, so you know how people comfort themselves. So that's why there are two terms. One is called NP hard. One is called NP complete. NP hard is the problem that they thought, oh, this problem are non-polynomial. They thought, because they cannot come up with a polynomial problem. What is NP complete? It's very interesting. I have one problem. I don't know whether it's NP or P. But there's another problem people thought is NP complete. So I actually can translate it to another problem. That means if I solve this, I can solve that. If I solve that, that means the two problems are the same. So I group this group of problem is called NP complete. It just means I cannot do the homework, but all those people before me cannot do the homework. That's why this homework is hard. It's just that. So they don't have a formal proof such that this NP complete problem is really NP complete. So here comes the part. If you can prove NP is not P or NP is P, either way, you got $1 million US. I'm not kidding. It's a real thing. There are 7 problems in the world, 7 mathematical problems in the world. You solve any one of them, you got $1 million US. I don't know whether they raised the price already. Okay. If you can solve that problem, remember me, okay? At least I have some commission, right? Introduce the problem, okay? But what I want to say is that's how real central computer science, the real ideal talking about, can we compute that or not, okay? And at last, there was a small joke because you say that
you need a break. Maybe you should take up that recent job offer to become a traveling salesman.
Because actually traveling salesman is the same problem. Traveling salesman means you have a graph, you do traveling salesman, you do visit every point with only once, okay? So this is a graph problem. Also here, I would like to show that you don't only solve the shortest path. Graph has a lot of problems. Like this is called Hamiltonian path problem. And next week, we will solve what is the minimal spanning tree problem. And the other one will show what is the if we have time left, we will show what is the network flow problem, okay, and so on. So there's a lot of graph problem. Actually, in NUS, before we have a 5,000 level course or 4,000, the whole course is about graph problem. Okay? Graph can solve a lot of problems. Yeah, so this previously, and there's some interesting question in the poll everywhere. Yeah, so for example, I wonder if chess analysis and both are use graph to calculate all possibility. In the beginning, yes. Actually, if you think about that, all the possibility of chess is not only a graph, it's a tree. At first, people think it's a tree, and later they become a graph, okay? Because you can actually have different way to form back. So they usually use a tree, and they actually use alpha beta pruning in AI. That was the original AI before large language model. People use tree to actually compute all the move for different way of chess and find. Okay, I only know that they can finish one by what's the game? There's one game called Forget Me Not. Oh yeah. Reverse it. Anyone reverse it? The Othello. There's one person actually did the research and they made a game called Forget Me Not. That means actually if you play the game, you surely lose one. Because they actually enumerate all the possibility and make sure you lose. Okay, yeah, and so on. So they actually, but on the other hand, for chess and like more complicated chess game like Go, you know, the Chinese, Japanese Go is too complicated. The space is too large for them to compute them all. So what AlphaGo can do is actually they also ignore a lot of other possibilities. That's why they still have a chance to beat the computer whatsoever. But I think human brains, the problem is we don't have that much space and computation power, okay? So, yeah. Do you agree with how Halim taught? What? How does he teach? He teaches very nicely, right? Yeah. But I think this is actually a small, not small, a small discussion. Okay, not argument actually. We actually think of because for data structure and algorithms, there are two big pieces. One is how do you understand, manipulate, modify, and create data structure. One is, once you have data structure, how do you solve it? How do you use it to solve problems? I would say both of them are equally important. But of course, we have all these SQL and whatever that we solve a lot of problems. So I will actually not answering this. I think Prof. Stephen focused on the problem solving part is also very good. But focusing on implementing is what our departments required. So that's why you also can see that I actually shift this to half and half or 4 to 6. So we have both of them in my course. And this is why I also bring up, I cannot answer something that our Prof. Banner also just answered that, okay? Answer why we need to teach data structure and algorithms. Yes, you can say that, oh, when we really go out to the job, we may not really need to like implement pointers. Okay, we don't need to write a linked list in the beginning. But how do those actually company pick you, to be honest? If everybody can do the same, how does a company pick you as an employee? Because everybody graduate with the same straight A, right? How do they pick you? So you must have something better than other people. So I would say it's a filtering process that if you know more about data structure and solve for a level problem, so yeah, you get better job. That's why we do have some, we have this tips program or whatever to help you to get better interview, to get better jobs, okay? So yeah, you can go to Ben's Facebook to have a look, okay? Yeah. Is today's we test for us the shortest path also? Yeah. Do you agree with Halim? I agree. Yeah. But I just agree doesn't mean totally will do it his way. Okay. I agree. He's doing well, and he's training people to do a competitive program. But do you want to be trained like competitive programming? It's very stressful, you know. Yeah. So I strike a balance. Okay. For those people who really want, you can excel in PE and get an A+, okay? That's why, just on top of that, the PE, take it easy, okay? I will say that the PE, I expect about 30% average, okay? Don't be too harsh on yourself because you already did very well in quiz 1 and quiz 2. Probably you guys won't be failing. I think, yeah, most of you, 99.999%, you won't be failing, whatever. So it's just you want to get an A+, please go for 100% in PE. I think in the history, I think I told you before, right? I guess in my whole history of almost 10 years of teaching C++ and whatsoever, there's only one person who get 100 marks in my PE. I mean C++ PE, okay? Is that a question you like to ask me? Actually, if you see all the past year questions, the first question is always linked list, right? So you just manipulate the linked list a bit in different ways. So yeah, and the second question, and usually is either hash table. I actually seldom do trees, okay, because trees are very hard to do questions, okay. Either trees or shortest path. Yeah, that's why you ask if shortest path is there. Shortest path or graph algorithm is easier to do. Yeah, but of course hash table is another one easier. I think you also prefer hash table, right? So I will do something like that. One year we even do union find. Okay, so by union find or heap. Okay, so 1 year we did heap, n-ary heaps. That means we do not binary, trinary heap, and so on, which is not, yeah. If you did your homework, it's not that difficult. Okay. Okay, thank you. If more questions, please ask here. Okay. Here. For details of the PE, we will actually email out and finalize after tomorrow. Okay. We'll put out the mock PE maybe tomorrow also for you to try to download. Okay. The mock PE is OT, okay. you do it yourself, no marks one. You can totally don't do it, okay? But if you want to do the mock PE, you need to download Exemplify yourself. That means you can actually go to the labs on next Tuesday without touching Exemplify before, which is quite dangerous, okay? You don't want to lose time in figuring out at the end of the day, how do I do that, okay? Hey, no, this one is not us, sorry. No, this one is last year. I don't do that, okay? Yeah, this is last year. You see, is yeah, this is not our course. You see how, yeah, it's July something, it's not us, okay? Yeah. Okay, what is this? Okay, let's come back. Shortest path problem. I hope you still remember what we did last week. We did Bellman-Ford. We did the Bellman-Ford. We tried to relax all the edge. Today, I need you to know how to do relaxation of the edge, okay? But if you forgot or you actually didn't watch the last week video, we just give a very brief introduction. Shortest path is like Google Map. We did try to find the shortest path. But again, I want you to understand that this is not only computing physical shortest path. Shortest path algorithm has a lot of like minimizing courses and so on, okay? So the basic question is, if you give a graph, all the edges are labeled with weight, how do you find the shortest path? Yeah. And the shortest path algorithm basically means for every vertex, like here A or B, I have something called estimated distance. That means during the flight of the algorithms, there will be some number, for example, 3 and 9, saying that, oh, until now, I presume that when I come from the source S to A, I need 3 units of time or 3 units of distance. That is my shortest cost. And to C is 9. So on the fly, we have a lot of this estimated distance for every vertex. And what we did is we have this relaxation process. That means I will consider an edge. Let's say if I want to consider edge AC, and you want to make a choice, because the edge AC is from A to C. So now you created 2 different ways to go to C now. One way is the original way, because the original way, I think S go to C take 9 minutes, okay? But now I know that from A to C is taking 4 minutes. The question is it faster I go to A to go to C, or I use the original old ways to go to C, okay? This decision and this process is called relaxation. Based on which one is smaller, you may or you may not update the estimated distance for C. Okay, so for each edge AC, can I improve S to C? So this is the relaxation algorithm we talked about last week. I'm not going to repeat that. Okay, so yeah. So this Bellman-Ford algorithm also we talked about last week. This is the hands-on Bellman-Ford. Yeah. So what we do is we do it n times such that we relax every edge. Again, last week say what is the meaning of negative cycle is SSFP. If about the shortest path algorithms, if I have a negative cycle, what does that mean? For example, it's in a sci-fic, right? It's like I don't know, science fiction. If I travel in the roads now to Changyi Airport, every road takes some minutes, right? This 5 minutes, that's 10 minutes. What if there's some roads you can go back to the past? Some road after you went to there, I start at 9 o'clock. After I travel through the road, it becomes 8 o'clock. Okay, can you do that? Of course, in real life you cannot. But what if we have such road and we can reduce time in that? Then I say, what is the earliest time I can reach Changyi Airport if I have a negative cycle? Then I can keep looping the route until when? Until you went back to Jurassic Age or the creation of the universe, right? You can go back. So If you have negative cycle, that actually means your shortest path algorithm is not meaningful at all. Okay, so we actually will assume our graph don't have that. So the Bellman-Ford summary for last week is very bad. It's V times E, and usually some of the graph actually V is equal to E is equal to V squared. Okay, so we talk about that. For the number of edge, the most number of edge can be V squared. Why? Because E can be mathematically we choose 2. Every 2 vertex choose 2. That is combinatorics, okay? We choose 2, we see 2. So that is E can be V squared. Very bad, okay? And of course, finally, we say that if negative cycle is suspicious, is there, you can use Bellman-Ford to detect it. Okay, if Bellman-Ford can keep relaxing more than V times, that's still relaxing, that means there should be a negative cycle existing. Okay. How do we improve it? V to power 3 is not acceptable, right? How do we improve it? First, I'm sorry to tell you that today we add a big constraint. We do not allow negative edges, not even cycle, okay? Let's assume we don't have negative edges, okay? So we assume that. And the shortest path will have no cycle, okay? And today's we do an even more clever way. This guy is called Dijkstra, okay? Dijkstra is a very famous, like our heroes in the past, okay? He actually come up with a very clever algorithms. Actually, you know, Bellman-Ford keep doing relaxation again and again. But is there any way we can relax every edge only once? But I try to find the right order, okay? That's what we try to do it today. And today's goal is, can there be any way I can relax every edge just by once? Good, right? Bellman-Ford is relax every edge V times, actually. So we just relax every edge by one time. So yeah, let's relax. Dijkstra is a very interesting guy, okay? He like to insult people. Anyone who, I think I mentioned a lot of time, right? Anyone knows Sheldon, right? Sheldon in Big Bang Theory, you didn't watch it. The geek one, always offend people, okay? He always offend people. He say, but there's some interesting quotes. There's some old times. For example, he's born in 1930, okay? Maybe even older than your parents. I think he's even older than my parents, okay? Yeah, so he said computer science is no more than about computers than astronomy is about telescope. I don't think now is applicable already, yeah, because yeah, that's what he thought like many years ago. The question whether a computer can think is no more interesting than question whether a submarine can swim. Of course, the computer can think, I think he thought. Yeah. There should be no such thing as boring mathematics. This is so seldom, okay? Yeah, let's go to the interesting one. This one. Anyone knows there's a language called BASIC before? Anyone programmed it before? When I was young, I did that. So he said that it's practically impossible to teach programming to students have a prior exposure to basics. A potential programmers are mentally mutilated beyond hope of regeneration, okay? Sorry, I learned BASIC before. But what BASIC did is BASIC is per lines, okay? They have line numbers. And what happened to BASIC is they don't have those functions. So everything is like in a script. You can, but I think the most biggest problem of BASIC is you can go to the code anywhere. That means you can jump up and down without any logic. Okay, that's why people are saying that bad. Yeah. COBOL also, he even says it's a criminal offense. Yeah, it's okay. You start insulting. The insult coming now. Okay. APL is a mistake. Carrying through perfection in the language. So this guy is very opinionated. This one. Object-oriented programming is an exceptionally bad idea, which could only originate from California. So he insults insulted OOP and California together. Okay, this guy. I don't agree. Don't sue me for that. Okay, yeah. So this guy is very interesting. Luckily, he died in 2002. Yeah, but this guy is very, very clever. Okay, you can see that not only this, a lot of very clever algorithm at that time is by him. Yeah. Okay. So how do we relax? Because if we want to relax it, it must have some order. Okay, can we relax? Let's try, explore. Maybe upon all the edge, can we relax the shortest edge first? For example, the shortest outgoing edge. Okay, so for S, have 3 edges. One is 3, one is 4, and one is 7. Let me relax 3. Now I relax 3, and I know that this estimated distance is 3. And I try to relax the next shortest edge, which is either one of the 4 or 3. Oh, we have a 3, so relax this. Are we done? Cannot, because you actually relax the distance of 8 and 6, which is you cannot recover them already. Okay. So first of all, sorry, failed tries. So we are not relaxing the shortest outgoing edge. And instead of relaxing the shortest outgoing edge, because the shortest outgoing edge is only one edge, the idea of the real correct algorithm is I relax the edge that gives me the shortest estimated distance from S all the way. Okay, let's see what does that mean. This may be a bit harder to understand. Okay, so in the beginning, I will show you the algorithm, how it works. I think it's better. In the beginning, let's say this is the graph. You got all the distances. And if you remember, by initializing the graph, every vertex, I will imagine that the estimated distance is infinity because nothing started yet. But of course, I start from S. S estimated distance is 0, okay? This is just a setup. And from now on, all those A, B, C, D, E vertex is actually this is the priority queue, okay? Later we'll know that this is a priority queue. It's there, but I just don't want to write them and repeat them. Okay, so remember that all the vertex with infinite distance is also in the queue. Okay, what do we do now? The algorithm is very simple. It's only one step. In this whole priority queue, I get the one with the shortest estimated distance and get out of the queue. Okay. For example, now, which one have the shortest estimated distance? Very simple, right? S. Okay. I guess out of the queue. But when I get any item out of the queue, the next, which is the remaining step, is I relax all its neighbor. Okay. So the algorithm is very simple. Get the minimal priority out of the queue and relax the neighbor. That's it. Okay, so I guess S out. And what are the neighbor of S? It's AGD, right? So I will relax SA, SG, and SD. Anyone need me to slow down? Repeat. Yes. Okay. So the priority queue on the right, you got all the vertices, right? And the priority depends on the current estimated distance. And current, you don't have anything. You only have S is 0 and other infinity. So who is the minimum? Very easy, only one S, right? So I do extract mean in my heap. S is being get out. But when I get out S, I will relax all the edge coming out from S, which is the neighbor of S. So after I get S out, I relax all the neighbors. So I'm not showing all those infinity. Those infinity is still in the stack. And I have this. Is it okay? From S to A, originally A have an infinite distance. But now I know that go to S is 0, S to A is 5. So 0 plus 5 makes A will have a new estimated distance of 5. That was what we did last week. It's okay? I need to slow down or repeat because it's probably the hardest step. The following is just the same. Okay, anyone want me to repeat? So now I relax A. The A will have an estimated distance of 5. G, 8. D, 9, right? Because originally AGD in the last slide, whatever they are, have infinite distance. Actually, in here, we still have other nodes. For example, like B is still in here, but it's infinite. C is still in here, infinite. I just didn't show them. Okay, they are still in the queue because we only care about who is the minimal distance. Okay, so far, now I have a new priority queue. And what do we do? Just repeat. What do I do now? I will extract the mean. Who is the mean now? Simple, right? A. What did I say? Extract the mean, relax the neighbor. So I extract A. What are the neighbors of A? A has 3 neighbors, right? C, B, and G. I don't move to the next line. What will be the new estimated distance for C? Who say the new estimated distance of C is 5? Who say it's 15? Who say it's 20? Correct, it's 20. Why? Look at this. I'm relaxing this edge AC, right? Because I relaxed all the edge. Actually, I will relax AB and AG later. I'm relaxing AC. What was the process? Remember that? The process of last time is I have an S going to A and S going to C, and C is infinite. So originally S go to C is infinite. S go to A is 5. A go to C is 15. So if I go to A and go to C, I know that I'm 20. And now is 20 smaller or infinite smaller? 20 smaller. So that's why I can update C to 20. Okay, this one will update to 20. How about B? You can tell me now. B is, who say it's 5? Who say it's 12? Who say it's 17? Right? So C will be 17. Okay, now the hard part. What is the estimated distance of G now? If you want to go from S to A to G, what will be the estimated distance if you choose this route? Yes? 9, right? If I go to A and go to G, it will be 9. Is it better than what I had already? The original what I had already is 8. And now I create a new route. Hey, this is a new bus route. Let's try that. But it takes 9 minutes. Should I do that? No. So that's why at this time, I will not change the estimated distance for G. G will remain the same as 8. Okay? And then I finish relaxing all the so-called the neighbors of A already. Okay? And after that, so I relax all this neighbor, all the neighbors of A, ta-da, become like that. Does it make sense? So the A's neighbor B and C are being added in. So B has an estimated distance of 17. C have an estimated distance of 20. And the estimated distance of G doesn't change. D doesn't change. That was already on the queue. Okay? Actually, if you can pass through this, you can pass through the rest. The rest are still the same. Now, which one should I extract from the queue? Simple, right? G. And what are the neighbors of G? G's neighbor are B and E, right? What will be the estimated distance for B now? Now is the hard part. Originally, B already have an estimated distance of 17. And what is the relaxation of the HGB now? If anyhow I go to G and then take this GB edge to B, what is the distance? Anyone? Just shout. 15, right? Is it okay? Is it okay? I go to G by whatever means I know, I don't care. Because somebody tell me I go to G is having a distance of 8. And now my edge go to G to B is 7. So that means I know that I already know a way to go to G by B by 8 and go to here 7. That's why if I go from this route, the estimated distance is 15. And the original way of going to B is 17. Which way should I do? 15 or 17? Of course, 15 okay? So that's why if you do that, in this priority queue, you update this to 15. Okay? And how about E? What is the estimated distance of E? So you relax the edge GE, right? And now the estimated distance of E will be 14. It's okay? And now let's change. So the priority queue also got changed. That is a new one, okay? So E got an estimated distance of 14. B got a new estimated distance of 15. And which one should I extract now? D, okay? Extract D. And what are these neighbor? This neighbor is G, E, and F. But wait a minute. This is another little trick. G is already out of the queue. Remember that? In last time, I already dequeued G. So do I still need to relax DG now? No need. Okay, so one of the things is when your neighbor already left the priority queue, you don't have to care about them. So I don't need to relax DG. And now I relax DE. So what is the new estimated of DE? If you go from S to D, it's 9. D to E is 4. And the total distance is 13. What was the old distance to E? 14. So which one is smaller? The new way is smaller, right? So I will update E again. And at the same time, I also update F because I can go to D to F with a 29 distance. So become like that. It's okay? The algorithm just goes. And now I go a bit faster, relaxing E. E is 13 to B is 1. So E to B will update this to 14. That means the new estimated distance of B will be 14. E is 13. And E to F is 13 also. So become 26. So F will become 26. Then update the Q. The Q is like that. And now I update B. B to C is 17. B to F is 25. So I can update again. And C update C to F is 26. That's why I don't update F. And then finally, F is the final vertex. It does not have any more outgoing edge. I can just dequeue it. And ta-da, all these red numbers are the estimated distance before they left the priority queue. And we claim that these are the estimated distance. Okay? So don't worry if you're still a bit not sure. We are going to do this exercise next week on the tutorial, okay? Done. And just now, if you remember the process, when you do the final relaxing edge, these are the edges that you finally relax your vertex. For example, this edge EB here is the last edge you relax to B. And these are actually the shortest path. This is the shortest path tree. So this algorithm does not only give you what is the length of your shortest path, it actually also gives you what is that shortest path. So if you want to go to F, you rather travel to D to E to B, then F is the shortest one. Instead, you go back to the graph. Oh, it seems that S go to G, go to B, go to F have fewer steps. But actually, the shortest path is S to D to E to B to F. Okay. And of course, we need to use a priority queue. And how should we so-called manage that? First of all, if you remember that, I need to insert an item. I need to extract the minimum. And the other thing, if you notice that I need to decrease the key. That means I need to get some of the estimated distance and reduce it if the relaxation improves the estimated distance, okay? So this Dijkstra, I have an edge of relaxation that I have the vertex, which is the source, W is the destination, the weight is the weight. So it's the same relaxation, okay? It's the same. Actually, it's nothing new here. If the original weight is larger than, you go to your source plus the weight of your edge, then you improve it. This is the same algorithm, okay? This is the same relaxation of last week. But here, I add one thing. If you do this relaxation and improve, I say that now the current destination have a parent that actually remembering the path. So this extra step is to help you to remembering the path instead of just computing the numbers. Okay, and of course, you can decrease the key because all the neighbors, the key will be decreased. Not always decrease, okay? They may decrease, and the priority queue may shuffle. Okay. And this is the weight comparison. Yeah, so you remove any vertex like G, and you relax this edge, and you need to make a decision. Okay, so you need to make a decision if 8 plus 7 is larger than the original distance of B or less. Yeah. So this is the parent part. If it is, then the parents of B will be G. This is the parent part. And you decrease B's from 17 to 15. So, okay, what is the running time of Dijkstra now? Actually, what is the very complicated operation? Extract mean, decrease key, right? You extract mean, decrease key. How many extract mean do you need to do? Extract mean at most is V, right? And then how many, what is the H operation of extract mean? Is log V. So is it V log V? Not yet, because after you extract vertex, you need to relax the edge. And it's a possibility you may need to change the position. So again, you depend on how many edge. So let's try. Who say is 1? Maybe I already have the notes, so you guys cheat. I just let go, okay? So it's 2. Why? Because extracting mean is only V log V. But after each time you extract it out, you may need to relax the edge. That means every edge you extract, so you relax once, which is good. But after relaxation of each edge, what do you need to do? You may need to update the vertex, which is decreasing the key, and updating that takes log V time. So the whole algorithm is V log V plus E log V. And of course, E usually dominant, and that's why delete mean is V times, and each node is add to the priority queue once. Relaxation is E times, and each edge is only relaxed one. Is it good now? Okay, each edge only relaxed one, but each of these need to operate on the priority queue, which is log V. So that's why at the end is, yeah, E log V. Okay, V plus E log V. Yeah, and yeah, so if you actually keep the parent pointer, it actually gives you the shortest path, not the shortest path graph. It's actually a shortest path tree. Okay, because we actually mentioned that the shortest path will not have a cycle. But why? How does this algorithm work? The algorithm based on a very simple truth. Remember, the vertex will leave the priority queue, the minimal one, right? The arguments I want to make is, whenever you dequeue one vertex, the vertex is carrying an estimated distance, right? That will be the best distance already. Okay, that means graduation. If you get out of the queue, you graduate. So, yeah. So, this is the base thing you want to prove. If I dequeue one vertex from the priority queue, it must be already reached its most improved shortest distance in the path. Okay, so let's see. Let's try to prove by induction, okay? Let's prove by induction by a more graphical form. So imagine that we have a graph, very complicated graph. All these vertex in this blue circle already dequeue, okay? Because induction, right? We assume that we already have a set of vertex that is already dequeued. And when they dequeued, we already also assume they already have the shortest estimated distance. And now I want to say that this vertex is the next one to be dequeued. Okay, this one is the minimum in the priority queue. I'm going to dequeue once. And the question is, if I dequeue this, what will be the situation that destroy our assumption that it doesn't have the best route? Okay, so I want to argue by contradiction, because there may be other paths that from other vertex then go to this dequeuing vertex also. Will there be any other path that can produce a shorter path, even shorter path? Let's argue that. Okay, it's another fringe. So the proof is, I want to prove that if you dequeue it, it's already the shortest path. And now let's begin. I try to argue by contradiction. What does that mean? When I dequeue this, currently this vertex have the smallest estimated distance. I let this distance be dv, okay? This is the current shortest distance. I assume this world is very rebellious. That is some other path that go from somewhere else have a distance shorter than dv. I try to prove a contradiction, okay? I try to say that this argument is not right. I actually don't like Dijkstra. He's a jerk, okay? He's actually wrong. Let's try to prove something that he has been thought right for many years. So let's win the Nobel Prize. So we thought that there's another path, this orange path, can produce a shorter distance. But then what does that mean? If it really happens, this real path will have a distance less than dv, right? What is the weight of this starting of this new path? Graphically, if the start point go to here, need a distance of dv, right? And let's try to bluff that this another route have a distance less than dv. But wait a minute, if it's less than dv, when we come to here, it's less than dv, right? What is this distance here? From this w to v must be some positive distance, right? Is it okay? Must be some positive distance. And then that means what is the estimated distance of this one? This one must be dv minus the whole length. That means this one must be smaller than dv. Wait a minute. If this guy is smaller than dv, if this vertex is smaller than dv, the estimated distance, what was the problem? Because we said now this one dv is the smallest one. How can you have another one smaller than me? So w should have dequeued before this vertex v. So w cannot have a distance shorter than dv. So too bad. That create a contradiction. Okay, let's go again. So if the real path that this, I will try to bluff it, saying that this distance on the orange side has shorter than dv, then the distance to w must be smaller than dv. That is smaller than the distance to v, and that's a contradiction. Why? Because this distance to v must be the smallest because you are dequeuing from the priority queue. Is already the smallest. So it's contradiction because P vertex V already have the smallest distance. So too bad. That's why the real path of this orange one must be longer than that. That means there's no such path is smaller than the original path should exist. Okay, there's a proof by induction because after you dequeue V and put it into a blue set, your blue sets keep expanding is another form of induction. Okay, so this is Dijkstra. Yeah. So finally, this is the conclusion of the algorithm time complexity. See whether you understand. Can we, let's say you have a graph. I actually know which stop is the start, which stop is the destination. Can I stop the algorithms when the destination is already dequeued? Do I need to search for the whole path? Let the whole priority queue all evacuate. Who say we can do that? Yes. Who say cannot? I must finish the whole graph. Why? That's exactly my last algorithm, the last argument. The other path cannot produce a shorter path, right? So that's why the answer is yes. When you dequeue it, already there's no possible way there's a shorter path. Okay, and think about this. That's how Google Map works. Google Map have the whole world. I just want to find a path from NUS to Changi Airport because I want to run away. Do I need to search for the whole map to all Malaysia, Asia, Earth to find that? Oh, finally my path to NUS to Changi Airport is the shortest. That means there could be a possible way I go to New York first and then come back is shorter. So the algorithm say when you dequeue it, is no. Okay, so that's why Google Map is faster in that way. When you actually have one single source and one single destination, you want to find the shortest path. As far as the destination is being dequeued, you are done. Okay, so, but on the other hand, how do we implement the priority queue? Of course, we can simply use an array. That array, a priority queue is OV, so it's not good. Of course, we can use the AVL tree or the heap we are doing, and all the operations because it's log V. That's what usually people do. But actually, there's another way called Fibonacci heap. Fibonacci heap is a very special heap that you will sue me if I teach it here. Okay, why? Because Fibonacci heap is a forest of heap that each of the heap size is according to Fibonacci numbers. So a Fibonacci forest is a heap that have one node, another one node, and so on. Okay, so they form a Fibonacci heap. That's called, but of course, not in this course. Don't worry. Okay, yeah. Next, hey, wait a minute. In the start, we actually assume there's no negative edge. Will Dijkstra work with negative edge? If I allowed negative edge, what argument will I destroy? Any suggestion? What was the proof or argument will be destroyed when I allow negative edge? Yes? Is what? Dequeuing the shortest path, and then, yeah, what will be destroyed? Yeah, dequeuing will be destroyed. Why? Why that cannot be the shortest path? Or why that may not be the shortest path when I dequeue it? Because I can go to other, you remember that just now? This proof. The proof is the orange root is larger than 1 or larger than 0. There's a longer path. But imagine that what if the orange path have some negative edge? For example, just now the proof is based on, oh, this one is the smallest. Let's say this one have a distance of 16. Just now the proof, because this is 16, the other one, let's say W must be bigger than that. Let's say W is 21, okay? That's why I dequeue 16, right? Because from 21 you go to 16 must be some positive root. That's why it's impossible to produce any other root that is shorter than 16 by now. But that is based on the argument, all the orange, the yellow node have positive edge. What if one of the edge here is minus 100? I can totally destroy the argument. I cannot maintain the argument because this yellow edge may produce another shortest edge to V now. Dequeuing V now is not so-called not safe at all. Okay, so the negative edge will destroy the whole argument. That Dijkstra won't work in that way. Yeah, but what if we really have some negative edge? If I run Dijkstra, for example, let me relax 4 and 10. I will actually make A is 4 and B is 10. And the next edge I will relax this relax to 5 and 5. But wait a minute, because A is already dequeued, the real smallest or the shortest distance from S to A should be here. And actually should make X is 1, and this is 2, and this is 2. This is actually the real shortest path. But because I just run Dijkstra, too bad. I fixed A to be the estimated distance of 4. I cannot relax it some more and go back. That's why the negative edge actually will destroy this. Okay, so the negative edge here will destroy the whole algorithms. Let's be clever. Can I? Okay lah, negative edge have problem, right? I make every edge not negative by adding a 10 to everyone. Do you think it works? But why? Why it works or not work? So no negative, right? I ask everybody to be 10. Why it doesn't work? Sorry? Okay. At the most negative lah. For example, I find all the path with all the edge. For the most negative 100, then I add 101. Okay, I scan through all the edges. I find the most negative one and add everyone to be positive. Can I do that? Let's say I can do that. But will this algorithm work? Remember, there was one deadly problem. In the beginning, I said the shortest path algorithm now does not depend on the number of hoops. One edge to edge. If you do this, what does that mean? Every hoop you add 10. Actually, the real distance will depend on number of hoops again. The number of edges you pass through. So if you actually do that, it's called reweighting the edge. It actually doesn't work. Let's say this graph, the shortest path to SBA is 1, SA should be 4. But if you actually even reweight it, it's still the same. You will still reweight this to be 14. But if you reweight the path of SBA, become 21. So it still doesn't work. It still relies on the 14, which is the original S to A path. You cannot go to the SBA path. So too bad. Dijkstra is a lot faster than Bellman-Ford, but it cannot handle negative weight. Okay, too bad. Okay, so pros and cons, depending on the problem. If your graph have no negative edge, definitely you use Dijkstra. But if your graph have some negative edge, sorry, you cannot use Dijkstra. Okay. Yeah. So going back, three brothers. Remember how we did depth first search and breadth first search? We say breadth first search is every time you extract a vertex, you put all this neighbor into a queue. Depth first search is you extract a vertex, you put all its neighbor into a stack. Dijkstra is the same thing. You take out every vertex and put all its edge to a priority queue. So these three are very similar algorithm, just that I will put them in the priority queue, okay? So breadth first search, use a queue, put all the neighbors. Depth first search, use a stack, put all the neighbors. Dijkstra, you put all the priority queue, okay? Three brothers. Yeah. Okay, on the other hand, what if I want to find the longest path instead of the shortest path? I just negate it. Can I? But D is negative path. Is it totally impossible? Who will say it's totally hopeless? Totally, no way. Whatever graph cannot find the longest path like that. Why? Why still there's some hope for certain graph? Go back to our last week's lecture. If your graph have negative edge without negative cycle, you still can find the shortest path by Bellman-Ford. Okay? But of course, only if your graph does not have a cycle, then you can use it to find the longest path. Because by finding the shortest path on the negative graph, that negation is the longest path. However, your path has to be acyclic, which means for general graph, go back to our video we showed in the first. Actually, in general, if you want to find the longest path for the graph, it's actually NP hard. Why? Because let's say if you, that's why the NP completeness come in handy. Let's say today, Prof. Allen can find one algorithm, I can find the longest path. Then I can solve the Hamiltonian path problem. Because the Hamiltonian path is the longest path of every edge is 1. Is it okay? Does it make sense? The Hamiltonian path problem is I want to find the longest path in that graph. Let's see if it's equal to the number of vertices. If I can solve finding the longest path problem in any graph, I can solve the problem of Hamiltonian path problem. So sorry, I'm not that smart, okay? So that's why solving the longest path problem is also NP complete. Too bad. Okay, that's XKCD. Anyone notice? It's an interesting comic. XKCD is from a romantic geek. Yeah, he got a lot of interesting comics that are related to very geeky things, but very romantic. Yeah. Hey, yeah, so here's other things. For example, the other problem, anyone know this knapsack problem? Knapsack problem meaning, for example, I have, this is the menu, and I have exactly this money. Can you come up with a combination of your menu that will combine to my price? It's called knapsack problem. And if you didn't know it, this problem can translate to the Hamiltonian cycle problem. This is a Hamiltonian cycle, if you can model the problem right. Okay, so that's why this problem is also NP hard or NP complete. Okay, for example, let's just show some other way, because I want to show you other ways of what problem can shortest path solved. Okay, in a few years ago, very popular topic in computer science research is human DNA sequencing, and how do we detect mutation and so on. Okay, so how do we model that? Actually, very simple. For example, if this is the DNA of a certain creature, this is the DNA of another creature. One thing you can do is during our mutation and evolution, the DNA is changing. So how do you know two species are close to each other? You just need to measure what is their cause of mutation by changing and just put them in the graph. Okay? So how much of this mutation? Because it's not just measuring how many difference in the DNA. You actually have some standard operation. For example, certain DNA changes allowed. So you can actually create a whole graph. If you can measure the distance between the DNA of one creature and the other creature, you actually can see how close these two creatures is. So it's a DNA alignment. Okay. The other, so you can actually measure that, is a shortest path problem. The other one is called scheduling problem. This one is harder to. This one I will delay it after our topological sort. Okay, because this one I will be more meaningful is topological sort, because topological, it will show that in the next few minutes. Is topological sort is talking about if you have some sequence, what should be taken after which one, then how do you align the sequences? Okay, I will talk about that. But this one is even a better problem. Then even you know the sequence, how do you optimize? I will come back to this, because sometimes I actually talk about the topological sort before that. So let's just spend 15 minutes talk about the topological sort. Okay, we switch to the topological sort slide. Okay, so this is another topic, but this topic is easy, so that's why I just chip in here. This is not only baking cookies, okay? This is actually all your running schedule of how to solve a big engineering problem. Later you understand why, okay? For example, these are the items or these are the tasks I need to bake cookies. However, there are constraints. For example, all these are steps, right? I must buy buy the eggs before beat the eggs, right? I cannot beat the eggs without the eggs. For example, I must beat the eggs before mixing the egg with the flour, right? So of all these tasks, there's some dependency. I must do something before that. And usually it's not about only making cookies. If you're doing your software engineering problem, or even just a big how to make an airplane, you have a lot of this dependency. You must finish this before that, finish that before that. It will be a very complicated graph. And what I can do is, I can actually model it with a graph. Each arrow means I must finish one before another one. For example, here, I must turn on the oven before putting the cookie in oven, right? I must have some dependency. So the edge meaning the source of the edge must be done before the destination of the edge. The question is, how do you come up with a single sequence that will make all this possible? What does that mean? That means, how do I rearrange this step? First, I go to shop first. Then I turn on oven. Then I beat the eggs. How do I make this sequence such that everything is possible? For example, I cannot say, let me clean the kitchen after a shop. Cannot, right? That is, I cannot do it because then according to my sequence, I must clean the kitchen after everything is done. So how do I come up with such a sequence? And if you see that, there's actually one very interesting phenomenon of this sequence. For this sequence, if you add back the edges in the graph, every edge must go rightwards, okay? Must go forward. You are not allowed the edge to go backwards. Because by backwards, it means this one must be do first before this one, which is not correct. Okay, so yeah. Is every directed graph can do such a sorting? Very simple question. Can or cannot? Huh? Can or cannot? Who say can? If you say can, I'll ask you, do you have chicken first or egg first? Okay, the answer is it may not. Okay, because you are not allowed to have cycles. Okay, I cannot have chicken egg problem. Okay, in order to have the chicken, you need to have an egg. In order to have egg, you have the chicken. You cannot have that. So first of all, the prerequisite is your graph cannot have directed cycle. And usually we call this graph without directed cycle, we call it a DAG, D-A-G, directed acyclic graph. Acyclic means without cycle. Cyclic means cycle. Acyclic means no cycle. Okay, so this one you can form a sequence, but this one you can, this one you cannot form a sequence because you have a back edge. On the right side, you can form a sequence because every edge goes to the right. Okay, so can you tell me, is this graph cyclic or acyclic? Hey, the answer is there. Okay, it's acyclic. Okay, although this graph have some rounding, is actually acyclic. So, okay, how do we actually compute a sequence like that? Okay, this one is called topological ordering. Can we use any of our existing method to do it? One very simple implementation is we can just use depth search. But wait a minute, it's not the real depth search, it's the reverse depth search. Actually, it's depth search, you output the thing with a reverse sequence, okay? What does that mean? If I do depth search, I search for this, I search for this, I search for this, I search for this. This is a sequence, right? And done. It doesn't work because the set timer now is after. So a simple depth search won't work too bad. So what do? Let's do a pre-order depth search. What is a pre-order depth search? Okay, that means I process each vertex when it's first visited. It's called pre-order. But a post-order means I process it when it's last visited. Sorry, this is all wording, okay? But let's see the diagram to see how it works. So a depth search, usually you do this, right? You visited it, you process the node, then visit your neighbor. This is called pre-order. Post-order means I visit every neighbor, then I actually output my node. What does that mean? It's actually very simple. It's easier to see a graph, okay? I still do a depth search. I also start with any vertex. Simply in layman term, it means I depth search until I reach a vertex. For example, I depth search all the way to take out cookies, right? And you reach a dead end. When you reach a dead end, that means you have no more neighbor. When you have no more neighbor, according to the post-order depth search, you output it. Ta-da! But you output at the end. Okay, it's the last thing I want to do. Then if you follow the depth search, you will backtrack to cookies in oven. Are you done with cookies in oven? Did you finish all your neighbors? Not yet. So you go to set timer. So set timer is the next one you did. And you go back to cooking in ovens. Good. When you backtrack to cooking in ovens, you finish. That's why it's cooking in ovens. So that's how you do it. So you do the depth search. Whenever you reach a node, all your neighbors are done, then you can actually output on a sequence. Then you actually backtrack to mixed flowers. But mixed flowers, you still have a neighbor of clean kitchen. So you go to clean kitchen. Oh, clean kitchen don't have any neighbors, so we can do clean kitchen. Then you go back to mixed flowers. Then you finish. Then you go back to measure flowers. You're done. So all these black ones are done already. And of course, if you remember that, depth search will start with every vertex again. So I will do any shop, stop. Oh, too bad, you have a neighbors. So I beat X. And now I'll go back to shop. And first, and turn on oven. Okay? It doesn't make sense. But according to your logic, it makes sense. That means I turn on the oven and then I go out to go do grocery. Probably you already bought the fire insurance of your home, right? Yeah, so, but according to the sequence I given, it's working. Unless, let's say, oh, maybe I want to add one more edge here. Maybe I want to add one more edge to make it safe. So I must finish shopping before I turn on the oven, okay? Then you create another order. Then you can actually do that. So this is called post-order depth search. Yeah. So the time complexity is just depth search, okay? So it's V plus E. Actually, there's another way, okay? Sorry, before that, do you think the topological order is unique? That means if you give you a graph, it always have only one way to do it. No, right? Why? Because for that, I can actually, for example, do on oven or shop, I can actually do turn on oven, then go to shop. I also can do shop, then turn on oven. Okay, for this graph, I can do some switching of the order, and the order still okay. This algorithm is called topological sorting. That actually gives you a sequence of work that you can label it out of your work order. There's another alternative algorithm, but this one needs a lot more data structure, okay? This one is very simple. Actually, it's more simple. Actually, it's still the depth search, okay? What it means is, if your graph have no cycle, your graph must have some node with no incoming edge. Does that make sense? A graph, every node can have outgoing edge or incoming edge. If your graph has no cycle, there must be some node without incoming edge. Must start from somewhere. Otherwise, you will create a cycle. So the algorithm is very simple. For those without incoming edge, that means they don't depend on other job. I can put them in my task. I do them first. I remove them from the graph. That's why this algorithm is a bit more complicated when you do a data structure, because you have to remove the vertex from the graph. After that, I have a new graph. Just repeat. Because after removing all the nodes without incoming edge, I will have some more new nodes without incoming edge. Then I just repeating that. That's the job. Okay. This algorithm talking, describing, discussing is easier, but implementation wise is harder. Okay. You can think about why is it? And this topological sort actually gives you a lot of application. Like if you have a very large software product or engineering product, you must have this type of dependency. So how do you come up with a work step that you do what, then you finish the job? Okay. And go back to just now our last, this one, the application. I just described it. I think this one may not be that easy to understand for now. This application is saying if you have a topological sorting graph, you don't only have which one should be done before or after which one. You have more. Each one must be done how long before which time. Does it make sense? For example, just now the cookies, right? You can actually, after turn on oven, you may need to wait 10 minutes for the oven to heat up before you put in cookies. Then, if you have more of this time constraint, more than you have a possible sequence, can you give me the shortest sequence? The fastest time you can actually finish baking this cookie. But the idea is actually very simple. For whatever edge, you just have to give some timing on that. For example, if B must be executed at most 10 minutes after A, I actually put a 10-minute time on the edge. And if the other way around, if B must be at least 10 minutes after A, I put a negative edge on the opposite side. And what happens is, after that, if I compute the shortest time, which is I do a starting node, I actually allow this starting node, this is a virtual node. That means it's an artificial node. I'll point to everyone, and I just find the shortest path by that, connect by 0. That is actually the shortest scheduling. Okay, so it's you can say this is a topological sort algorithm plus. It does not only give you the possible time for you to compute everything, it actually gives you the shortest time to compute everything to finish. Okay, so this one is not that easy, but this one is must use Bellman fault because this algorithm actually includes negative edge on that. Okay, for those who really want to pound this problem, we can discuss further. Okay, but I think this one is a bit not easy because I talked a bit too fast today. Shortest path, then topological sort, and go back to this scheduling. Okay, we will discuss more about this maybe in the tutorial. Okay, so okay, that's it for today. Any more questions for the poll everywhere? Oh, what is your coffee order? This one is just the canteen one. Actually, the depends on which one. The other one is the LT91, the very good coffee uncle, right? Yeah, but I don't have discount. Okay, too bad. Oh yeah, Crystal is finishing. Don't worry. Between probably today, I almost finished already. Yeah, thank you. Yeah, thank you for treating me. Yeah, but quite good lah. Crystal quite good. Don't worry. Okay, thank you. See you tomorrow.